Well, thank you. So I'd like to also thank the organizers for inviting me to this wonderful, now traditional meeting here. I'm really enjoying the wonderful environment here and the physics at this meeting. So what I want to present here is some progress in studying gauge symmetry constraints in theories that should be consistent quantum gravity theories. So we expect that when quantum field theories are coupled to consistent quantum gravity, they should be subject to some additional constraints beyond that of the standard quantum field theory. And this consistency condition, searching for them systematically, is encoded in the swampland program. On the other hand, we have string theory, as of now, still the only game in town as a consistent theory of quantum gravity. And globally consistent compactification of string theory, which, as I just said, also automatically include now also quantum gravity. They impose additional constraints as well, which emerge due to the compactification. And so the geometry of compactification space imposes additional constraints on this consistent theory of quantum gravity. If this geometrical constraint were really completely encompassing all the conditions that we would get on consistent quantum gravity, that would imply that string theory is indeed genuinely the only game in town. And as a card-carrying member of string community, I'm genuinely hoping so, that string universality in some form will eventually prevail. But here I want to focus on finding really more of bottom-up physical conditions that indirectly would be reflecting these geometric constraints of consistent quantum gravity. But I do not want, these physical conditions to refer directly to string theory per se. So this program actually has by now quite a long history with important progress primarily in higher dimensions on constraints of consistent quantum field theory. And in this talk, I want to highlight two specific directions. So in the first part, I want to highlight constraints on the gauge symmetry topology for minimally supersymmetric a-dimensional supergravity theories. And what we will see is that this will be closely related to gauging of OneForm symmetries there. I would also make a long digression where actually in top-down approaches, namely refining string junction approaches, we believe that we have completed the whole analysis of global constraints for string theory vacua in A dimensions. Okay. In the later part, if I have some time left, I would also like to touch about on another interesting phenomenon which has to do with automatic enhancement of gauge symmetries, and this would be minimally supersymmetric supergravity theory in 6 dimensions. And we'll see that the conditions of gauging of flavor symmetries in ineffective theory or properties of BPS string defects there enforce this, from the outside perspective, somewhat unexpected automatic gauge symmetry enhancements. So the guiding principle that I'm going to employ here are first from geometry. So the constraints from geometry will primarily emerge by looking at F-theory compactifications. And then I will turn to physics arguments, which will focus in particular in the first part of the analysis on gauging OneForm symmetries, higher form symmetries, So namely, if we see encountering the effective theory, global gauge symmetries, including higher form symmetries, we expect them to be broken or gauged in consistent theory of gravity. So implementing in the physics analysis really the analysis of higher form symmetries and no global symmetry hypothesis. Okay. So the first part of the work is based on a program together with Marcus Dirigal, former visiting postdoc at Penn, now assistant at LMU, Ling Ling, formerly postdoc at Penn, now at CERN, and soon to be in Oxford, and Hao Zhang, a student at Penn who actively works not only with me, but also with Jonathan. So the first thing that I want to highlight is the origin of this physical arguments, how a global topology of gauge group in 8 dimensions is inherently related to gauging of one-form symmetries. We have also addressed this global symmetry constraints from the F theory, from the string theory perspective, in particular in MF theory duality context, going down to 7 dimensions, and also arguments in 5 dimensions, but also direct top-down constructions of AD CHL vacua, and most recently, the full analysis of 8-dimensional and also 9-dimensional string vacua via string junction techniques. And this will be the second part that I would like to highlight. Now, if time permits me, the second part of the work is based on automatic enhancement in 6 dimension, is based on work with Ling and also with Andrew Turner, formerly from student at MIT, now at Penn, and there's some work in progress, but I anticipate I'll have to be very brief on that. Okay. So let's proceed. I mentioned already that from the string theory geometry point of view, I'm going to employ F theory. So though this is not a community to explain what F theory is, I'll just briefly highlight some of the things on F theory compactification. As we all know, this is a powerful framework where we geometrize axiodilaton as a modular parameter of 2 torus, thus manifestly demonstrating SL2Z symmetry of type 2B string theory. And when we are talking about F theory in lower dimensions, we are talking on compactifications, on elliptically fibered singular Calabi-Yau few folds, where in codimension 1, the singularity that is encountered there is associated with a non-abelian PQ7 branes, and the type of singularities that this vibration encounters, namely ADE singularities, specifies the non-abelian gauge group symmetry of this compactification. Another intriguing property of F-theory compactifications is that elliptic fibrations, namely elliptic curves, carry also intriguing arithmetic structure associated with the Mordell-Weil group, whose rational points or in the fibration sections specify abelian gauge symmetry factors, and the torsional points, torsional sections, are associated with the appearance of global topology structure. I just can't help myself and point out this part because actually, you know, the techniques of F-theory compactification enabled us actually go down all the way to 4 dimensions and deal with n=1 effective theory. And this is associated with compactification on elliptically fiber Calabi-Yau fourfolds, and a specific elliptic fibration allowed us to found really the complete standard model gauge group directly that involves both non-abelian factors and the abelian one associated with the free part of Mordell-Weil group. And furthermore, we could also fix the gauge group topology there, in this case by studying the so-called Shioda map of Mordell-Weil divisors that fixed geometrically for us the topology of this group. Now, advancing the toric geometry techniques, namely studying the basis of these fourfolds, three-dimensional complex basis to be toric, along with further consistency conditions of fluxes, we arrived at unprecedented number of standard models with the exact chiral spectrum of the standard model, namely 3 families of quarks and leptons, and in addition, in this particular case, also with gauge coupling unification. Well, this is by now an old story, and the hard thing is really taking place now for over 2 years already, because we don't want to deal only with the chiral spectrum, but also want to determine quantitatively the exact mass spectra in these compactifications, including the number of Higgs pairs. And some of the progress that was made was actually posted yesterday on the archives, where we study matter spectra in this compactification that happen to be associated with so-called root bundles. Namely, those are fractional powers of anti-canonical divisors restricted to metacurves. And so the study of root bundles on such metacurves, it's really extremely difficult problem. Nevertheless, we identify a large number of F-theory QSMs that have geometries without any vector-like matter exotics per se. And for that, we actually had to go to advanced aspects of root bundle analysis, which is really dealing with what is referred to as limit root bundles on nodal metacurves. Namely, we deform the original metacurves of this compactification to nodal ones, where we can, by techniques developed by mathematicians, we can study really all the allowed root bundles that this particular compactification leads to. And so we actually develop on this nodal curve the limit root cohomology study for examples of nodal curves that are of so-called tree-like structure and actually give us fixed number of cohomology for specific compactification, and it's independent of triangulation. And the remaining typical examples could result in so-called circuit-like nodal curves, and even those have a generically a fixed number of cohomologies, except for few examples that we have to handle by hand, the so-called jumping circuits, where we can see the jump in H0 cohomology when the nodes of these curves are spatially aligned. And these jumps actually mirror somewhat this classical Brühl-Noether jumps on the smooth curves. So it's sort of an interesting phenomenon itself. And we could do the complete analysis of all root bundles for this particular polytope that has 10 to the 11 triangulation, and find that all the root bundles on this nodal curves have really H0 equal 3, and thus no vector exotics. One can extend the analysis to other ones. We have more statistical analysis where H0 equal 3 is really most prevalent. Okay, but we also find some other sub-examples where H0 can jump to 4. But it's a somewhat interesting answer that this is at least for this example, we are dealing with complete cover of the whole set of compactifications associated with single polytopes, which has inherent connection actually also to independence, to triangulation. But I spent too much on that. The outstanding thing is really Higgs nodal curves. They are much more complicated, work in progress. Okay, now back to the lowbrow approach, namely, let's go back to what I was referring to, is really focusing on global gauge group topology in A-dimension n equal 1 supergravity. And I'm going to first take the insights I get from geometry, from string compactification. And I'm going to choose, I want to highlight first how we are dealing with the actually global structure of, say, certain non-simply connected non-abelian gauge group G, and the corresponding global structure, which is discrete valued group Z that sits in the center of G. And for concreteness, I'm going to really choose a specific example, which is a product of SUNI factors, where the center is analogously related now to product of ZNI factors. And I want to study now the subgroup of the center that determines the global structure, namely Z, whose generators will be represented by certain integers that sit in the corresponding ZNI centers. Okay. So I'm in A dimensions, so let me go now to geometry to study global structure of compactification with that type of non-simply connected non-abelian factors. And so I'm going to do F theory, and I go on elliptically fibered K3, which will give me n equal 1, d equal 8 supergravity effective theory. So as I already mentioned, in F theory, compactification, the topology of gauge group is encoded in the geometry, namely in the Mordell-Weil torsion. In A dimensions, this can be really analyzed over complete set of elliptically fibered K3s. And for the example, when compactification leads to the gauge group algebra of a product of SUNIs, the mathematicians, using arithmetic techniques, determined that the global structure associated with this Z, global symmetry specified by generators Ki, okay, has the property that the combination of Ki's and Ni's of SUNI in the specific combination has to be integer. So all these compactifications based on this gauge group algebra actually produce the following constraint on the allowed global structure. Okay. So this was very intriguing. One stared at this thing, and you would like to find out the physical argument how this, where this constraint would be coming from the physics argument. And so let's turn to physics. So physics constraints will turn out, as I was alluding already, will be related to, in this particular case, to one-form symmetries. So in the field theory, it was realized a while ago that if we are dealing with the global topology G mod Z, then there is there are discrete values one-form symmetry that acts on line operators. Okay, and so if we want to deal now with such a field theory in consistent theory of gravity, this global one-form symmetry has to be gauged. Otherwise, this is not a valid description of the consistent theory of gravity. Okay. So let's turn now to actually the properties associated now with this one-form symmetry, gauge one-form symmetry. The non-abelian gauge group factors have fractional instanton density, and under the one-form symmetry action that is associated now with the two-form discrete valued gauge potential C2, transform field strength by the C2 two-form potential. So when we are looking at the instanton density calculation, one sees that the field strength actually for of this instanton background is related to Pontryagin square factor and a factor, prefactor that is typical fractional. So that's where fractional instanton come from. Namely, for SUN, it's the factor that is n minus 1 over 2n. Right. So since we are dealing with supergravity theory, this instanton density, namely trace of f square, in supergravity theory couples to a tensor four-form potential that is part of the supergravity multiplet. And this four tensor before enjoys the large gauge symmetry, and it couples in the Lagrangian to the instanton density via this, well, Chern-Simons type coupling of before wedge f square. So it's this term that is a source of potential mixed gauge anomaly, and thus U1, so mixed U1, a large gauge symmetry, and the corresponding one-form symmetry. So it's clear that under the action of this large gauge symmetry and one-form symmetry, this contribution to the Lagrangian produces in the path integral, in general, a non-trivial phase, which is combination of, for particular product of SUN I factors with the gauge global one-form, with the local one-form symmetry Z. This contribution is of that form. It is Ki square because it's Fi square, and then each SUN factor will produce for us the corresponding fractional instanton number, which is written in that form. Okay, so to have this anomaly absent in the theory, this factor has to be multiple of Z. Okay, so to be allowed to gauge now this theory, we should not have this mixed anomaly, and this factor should be integer. In physics, this gauging of one-form anomaly produces this condition on the mixed anomaly, and lo and behold, that's precisely the factor we got from geometry. Okay, so that was really intriguing thing. So we can go on and see what are further implications of this gauging of one-form symmetry, and one can study now examples not only of a product of SUN factors, but also exceptional examples, and one can relate this fractional instanton contributions similarly to gauging on one-form symmetry by writing these contributions as a sum of specific SUN subgroups. But just to go back to this product of SUN I factors, this really is quite constraining. So if we focus on examples of a-dimensional theories with rank 18, we see that if for a single Zn factor, Zl factor, when L is bigger than 8, there are no anomaly-free solutions. For L equals 7, for example, it's unique. For N equals 8, it's unique. So we see very much constraining the allowed global structure of the gauge symmetry group. Okay? We can also ask ourselves, how about other allowed gauge group factors with rank 10 and rank 2? And examples of rank 10 arise as string vacua of CHL strings, and they also match precisely this OneForm gauging arguments. And more recently, we also looked at compactification really covering global gauge group structure of all the string compactifications to 8 dimensions via string junction techniques that include actually a new construction with global constraints for rank 2 case. And that will bring me now for a long digression. Okay, so I still have a while, I think, since we started late. So let me go on to a long digression about this refining string junction constructions in 8 dimensions to get a handle on the complete global constraints of the allowed gauge group topology. Okay, so just to remind you, string junctions are string prongs between PQ branes in F theory language, and they are in one-to-one correspondence with geometry of the 2 cycles wrapped by the strings. So if we look at the perpendicular 2-dimensional transfer space, namely that's the one we will compactify eventually, the string junctions are built out of so they are built out of one-dimensional oriented prongs between different string stacks, and some prongs that can go to the boundary of this non-compact space. So I mean, if we, in the non-compact version, or local version, we see string junctions as prong that start and end on stacks, and they could be identified with the roots of the resulting gauge algebra lattice, and the corresponding external prongs that asymptotically end on the boundary are associated with the weights of the gauge algebra lattice. A similar story goes for magnetic junctions. Now we are dealing with 5 branes that wrap 2 cycles, so those are BPS 3 branes in target space, and so we realize also the related AD algebra with weights and co-weights the same. So if we are talking about now weights modded out by roots, this, as I was arguing, is equivalent to dealing with non-compact 2 cycles, modding them out by compact 2 cycles, which at the end specifies, in the case of a single non-abelian gauge group factor, the center of this non-abelian gauge symmetry, and this is precisely related to magnetic or electric chiral symmetries. We can now continue. Our goal would be to really build now local string junctions, namely on non-compact geometry, and determine gauge group topology there for local examples. And so in particular, the building blocks are what I refer to as non-root junctions that carry non-zero asymptotic PQ charge. They can be built out of 2 parts. One part is associated with a gauge representation, namely out of root prongs that are fractionally charged. So that would specify the charge under of this junction under the gauge symmetry. And then there is also we split that into that part and the part that is captured by the monodromy of this junction that is associated with the extended weights of the so-called fractional loop junctions. So they specify the monodromy of junctions, and the others, the representation under gauge symmetry. And so in particular, this fractional loop junction can be represented really with this loop that then ends up at the end asymptotically in the junction that have total asymptotic charge PQ. Okay. Now those are the building blocks locally, but now we have to go to the global compactification and see how we constrain gauge group topology there. So the automatic, the main argument, of course, is in compact context, we cannot have any asymptotic net PQ charge. So this restricts our analysis by gluing disallowed fractional patches of string junctions, by gluing them in such a way that the resulting configuration is encoded in the fractional null junction of 5 branes, which will then in turn determine for us the global topology of the gauge group. So implementing that, okay, allows us to study the global constraints of all rank 8 vacua, and this is an example, for example, of a rank 18 vacuum and the corresponding global structure, which comes from the constructions of these fractional null junctions in the magnetic frame. We can also extend this analysis by looking at a billion factors, so really covering all the allowed topologies of rank 18 constructions. And now the part that's important is how about things beyond F-theory picture, namely junctions on O7 plus branes. And the problem with O7 plus branes is they do not split naturally at finite G string to PQ branes. And so one understood that the monodromy of this O7 planes is the same as the one of SO16 stack, but effectively there is a non-trivial flux that freezes the singularity in the MF theory language. So the fact that this freezing of O7 singularity really does not depend on global constraints. It's really a local phenomenon. So we proceed by replacing the SO16 stacks or one stack with O7 branes, or in principle, which would lead then for us to rank 10 construction, or 2 stacks of O7 branes, just by technically replacing that, which would lead to rank 2 constructions. Okay. Another important constraint is that this O7 planes impose constraints on strings that end on them. Namely, they have to have even P and Q charges. Okay. The corresponding magnetic ones do not have these constraints. One can derive these constraints actually directly if one assumes that O7 planes are dual to CHL vacua. In this case, then from CHL vacua, we see that this constraint is derived under the assumptions that one O7 plane is in the constructions of CHL vacua. Okay. So now we impose the global conditions, and our information on total global constraints emerges. So we get actually the examples with just one O7 plus brane, which leads to rank 10 vacua, and the new, those are first constructions that were not done by any other technique, which are related to 2 O7 plus and are rank 2 vacua. Okay. So I'm running out of time. Unfortunately, it's going not as fast as I was hoping. But I do want to highlight that actually this technique allows us to uplift these constructions to 9 dimensions at the boundary of 8-dimensional compactification, and actually allowed us to sharpen the swampland distance conjecture in 8 dimensions. Okay. So what we heard yesterday in a beautiful talk by Timo, that specific infinite distance limits of F theory on K3 moduli space describes 9-dimensional n equal 1 theories of rank 17. In the string junction picture, okay, the appearance of this a limit to 9 dimensions is associated with appearance of singularities on the boundary of moduli space with affine algebras being part of the construction on the boundary. Namely, if we have, for example, affine algebra En, if we have just En algebra in the construction, actually when we go to the boundary, we have to, in this limit, put another brane on top to enhance that into this affine one. So in this construction now, we see that we get in rank 17 2 series, as was probably also mentioned by Timo, that are now associated either with SUM factors and 2 affine branes, and then SO with 1 affine brane, and then so this is the boundary of 8-dimensional space. So in 9 dimensions, we get the corresponding surviving groups with affine nodes being stripped off. And so those are actually all the maximal non-abelian enhancements and are related also to 9-dimensional heterotic vacua. So in the last part, okay, 4 minutes. So in the last part, what is really beyond this analysis in our case is that we can now have 9D uplift with 107 plus brane that produces for us rank 9 constructions. And so now in this case, what we were doing is, let's say we start with the ADKs with just 1 affine factor. And so in 9 dimensions, right, this becomes, in the limit becomes ordinary EK factor. And now we want to look at this series and freeze at either SO16 that is inside SO or E8. So those were constraints on the global consistency of this construction, and we had to actually freeze E8 affine node. So it is the one that has to be frozen. And that then led for us to only, now also with SU part, when we have two ones, we end up now with, in this case, with SO18 cases, but now we have, for SU chain, we still have 1 En left in this construction, and that can be also verified in 9 dimensions from related studies of CHL string. Now, when we uplift 2 07s to 9 dimensions, we are dealing with rank 1 compactifications, and now we have to freeze 2 E8 affine nodes, and so that brings us really down to the gauge group SU2, and it is well known that actually the global structure has disconnected moduli branches, and actually with our analysis, we saw how these disconnected 8-dimensional branches are really connected through D equal 8 vacuum construction, and so all 9D string vacua are emergent from AD constructions. So I said I knew I would have very little time, but let me just read this a bit too long. digression, but I think it was sort of crucial because there are some new aspects here via string junction construction. I would now turn back to some further physics comments, which has to do with the consequences of this one-form symmetry constraints to be either gauged or broken in consistent theory of gravity. So clearly, the lattices are different if we have original non-abelian gauge symmetry or whether we have the one with the topology G mod Z. So in particular, G lattice definitely has states charged under Z. Okay? So if anomaly is present for this particular one-form symmetry, it has to be broken. Okay? And a gauge group turns out to be G. So consistent quantum theory should really supply for us the necessary states somewhere that are charged under Z. And we would search for them then in the dual BPS D3 brane spectrum, which is actually a very hard problem. So that's comment on breaking versus gauging. Another thing is also, I should point out, I stayed in 8 dimensions, but there is extended efforts also in studying mixed one-form gauge anomalies in dimensions less than 8. In particular, as I mentioned, in FM theory duality down to 7 dimensions. Okay, we saw the importance of the origin of this symmetry due to torsional boundary, G4 flux there. In 6 dimensions, as it was studied via excitations, now in this case, of BPS strings. And so also FM theory duality down to 5 dimensions and important other works related to that. Last but not least, I want to mention that this mixed, in our case, one-form gauge anomalies they didn't have actual gravity in it. So there should be important aspects there directly also in CFT theories and should have important implications for CFTs in 6 and 5 dimensions, and some of the things related to that were also in Linkstock. So clearly, I wanted to say more about this gauge enhancement in 6 dimensions, but I'm running out of time. Yes, I am. I just want to say that whatever symmetry you see in 6 dimensions, if it's global, you better gauge enhance it. And this was the origin of this geometric automatic gauge enhancements that one saw in F-theory construction, and we explain either via gauging of the resulting flavor symmetry in the effective theory in this particular examples, or we saw this complementary story also by studying the anomaly inflow associated with the BPS defects, strings, E strings, or other supergravity strings. So summary, as far as physics of a-dimensional one-form symmetry goes, I think we're really zeroed in completely on it, in the sense that on physics, it's gauging of one-form symmetry, and it's in perfect agreement with all that we know from top-down construction, including this most recent one via string junctions. Story here of the 6-dimensional gauge enhancement, it's murky. We have examples where we see how this phenomenon happens either due to gauge flavor symmetries of effective theory or on the BPS strings, but there are examples we cannot really completely nail, so this is just some explanation. Well, future directions, yeah, it would be important to understand actually some of this non-trivial automatic gauge enhancements in 6D with some other phenomenon that is not in the flavor, gauging of flavor symmetry. Also what we encountered is the importance of string defects, which are now really somewhat more general because they are really defects in 6D, in the 6D bulk, and SCFTs associated with these defects are really not well studied yet. So it's clearly an open question. A natural thing one would want to ask, of course, how about in 4 dimensions? What are remnants of constraints of that type that we saw in higher dimensions? And we expect that maybe axionic strings play an analogous role in this context, but I don't have much to report on that. And to understand better, higher form symmetry may be associated with this axion dynamic would be interesting. Is there a role in string compactification? Big questions. Okay, so thank you. Thank you for your patience. And I would like to conclude, just now make the announcement so I don't forget. So I put myself on the spot that the next meeting will be at Penn. The time will be is not fixed yet, but it's likely to be a spring break, which is typically in March. Thank you. Thank you.
Use the 60 anomalies that you have that has to be, not anomalies, symmetries that has to be, global symmetries that has to be gauged to put bounds on which SCFTs can be part of the compact theory?
Well, I don't have a good answer, but maybe Lynn can say more. Yeah. Yeah, constraints on compact, SCFTs in compact. Yeah. Yeah, so, okay, so in case, yeah, I don't have answer to that, sorry, yeah.
I see Miguel and I see Sakura, and Paul, you put up your hand later, so.
Mine is very, very quick. So you found the development of each group in the rank 2 from one model case in 8 dimensions, right?
Rank 2, yes, yes.
So I just want to, so there's a one which has SU2 plus SU2 algebra. Do you have, what is the global form that you get there? Is it SU2 plus SU2 or is it SO4?
Yeah, we get, I believe it's, yeah, it's modded by specific factor. I would have to look this up, but it's completely specified, right? Because I tried to argue, yeah, we get them, but now you put me on the spot, I'll have to look up on the table. By the way, it's in the appendix, and it's over 5 pages, rank 7, well, this is now, no, this is 9D, but also, yeah, it's completely fixed. And as you know, there are very few examples there, yeah.
Is it clear that disconnected H groups are excluded? Can you explore that?
Sorry, disconnected? No, that's a very important thing. That's an elephant there still, because, no, we have not. Because, you know, natural question you would ask, where is discrete zero form, where is the 2 group and all that? Because all I did in this very simple example in AD, when everything is just in a joint representation, right? Picked up the simplest thing that works. But that's very important questions to be addressed, yeah.
Okay, maybe let's take
Okay, thank you.